Thank you for joining today. This is the fifth NUEGO webinar in our monthly webinar series. The webinar series is a engineering discussion, generally two engineers, about things we're doing at NUEGO here. My name's Ben Hoffman. I'm going to be presenting today on our NUEGO Network Toolbox for MotoHawk and also some general things on CAN development. During the webinar, feel free to ask questions. There is a question panel on your GoToWebinar dialogue interface, and if you ask questions there, I'll try and answer them either during the discussion or at the end. So feel free to ask questions. So the NUEGO Network Toolbox is a library that we make available for use with MotoHawk to use CAN DBC files in your model. So to date, the way that CAN has been done with MotoHawk is using M files. So there's a format that was defined for use with MotoHawk to specify all of the details about a CAN message. And this was designed around 2004 or so to allow a single file to specify the interpretation of a CAN message for both the sender and the receiver. So you'd have two nodes, maybe more, communicating on a CAN bus, and because they share the M file, they are able to properly interpret both from the sending side and the receiving side all the details about the CAN message. And we found that was a very useful way to cut down on translation errors where a receiver doesn't have the same specification as a sender. But that kind of required two nodes to both be MotoHawk because they would then share that file format. As CAN became more prevalent in the controls space, CAN DBC files, which is a vector file format, became the standard way to specify CAN messaging. So you, if you were going to supply a canned network component like maybe an electric power steering pump, we'll say, you would have a CAN DBC file that would specify the CAN messaging that you're sending and expecting to receive, commands or something. The DBC file would be provided to those people that would be communicating to you, and so this was a great way to cut down on translation and also, as an industry standard, allowed for a common file format among participants in a network control scenario. So what I'm going to do is I'm going to first kind of talk about the MotoHawk tool and how CAN was done before, and then I'm going to talk about DBC files, and we'll create one, and also show one that is a pre-existing one, and then we'll work through integrating the Network Toolbox product that we have into a model and doing a build and looking at some CAN traffic on a network. So the tool we're going to talk about today you can find on our wiki site at neweagle.net, and the DBC to CAN Network Toolbox is here. So when you get the product, you'll get an installer, and so I'm going to go ahead and go through the process of installing this tool. So I've got the installer here. It's an exe file. So I can run that. It installs into my program files, and this is an important piece here. Set the MATLAB path. What this will do is it will integrate the Network Toolbox into all of the MathWorks versions that you have installed on your machine, and it's important if you install a new MathWorks version, you're going to want to go ahead and rerun this installer. So it installed, I have several versions of MathWorks tools installed on my machine. This is my development machine, so I have to work with and test with a lot of different versions. So I went ahead and installed that. I'm going to go ahead and open MathWorks now. I'm using MathWorks 2012A here. This tool is supported with pretty much all of the different versions that work with MotoHawk. So you can see here now that I've run the installer, the New Eagle Network Toolbox is initialized. You'll see that to kind of confirm that it's installed. So I'm going to create a MotoHawk template project that we can look at to do our work today. And this just creates a simple MotoHawk project that is, it contains some basic elements that you'd want to have in your model. I'm just going to clean it up a little bit so it's easier for us to work with. So basically I have an empty project now with target definition and one time-based trigger. I'm going to change my target to the one I have on my bench here. Okay. So inside the folder here, the template project comes with some folders that are included on the path, an images folder in case you want to include some images in your model, a libraries folder. This is useful if you're using some of the starter libraries that we provide. We've got a MotoHawk Foundation library that includes a lot of primitives that you might want to use in your model, like a PID controller, just things that we found to be useful. So we provide that, and you can find that on our wiki. Here's the one that we're looking at today, CAN, and I'm going to open this file. This is the M file I was talking about earlier. This shows the format that was used in the past to specify a CAN message. So you see things like what bus is it going to be on. You can specify the ID and masks, and then you get down to specifying the individual fields. So in the past, the way that you would specify a CAN message was to go ahead and go through each of these M file, create an M file for each message, or you could put multiple in one M file. But for each field, you have to specify the name, units, the start bit, and scaling, and endianness. And then when you have this defined, obviously this works with MotoHawk modules. But if you're working with a non-MotoHawk controller, like a component you may have sourced that you want to control over CAN, you'd need to create these M files for each of those each message for that component, and you may be interpreting a Word doc or an Excel spreadsheet or something, and there's definitely a lot of opportunities for misinterpretation there. Due to the way that people specify start bits and endianness, it can be there's some room for interpretation sometimes with specs. They can be kind of ambiguous. So the industry moved kind of to this DBC file format, and so what I'm going to show here is this is a free editor from Cavassar that we use. Various other vendors also have DBC file editors. This particular one you can download for free on Cavassar's website here. Just go to downloads and type database here. There's the database editor. It's a standalone editor that you can download for free, and then there's the user guide there. So if you're going to be working with DBC files and you don't have a preferred tool, this is a good one to start with. So for our purposes today, we're going to create a DBC, but you may, as I said before, you may acquire one from outside, and I've got a DBC file here for J1939, and this is quite a large DBC file. It contains the application messaging from J1939-71. And one of the most common messages that people look at is the one that contains engine speed here, EEC1. We can look at the IDs in hexadecimal here. This is PGN F004, and you can see here it contains engine speed. Now this particular editor, it's nice because it shows you over here where in the data field for this message the data for this particular signal will be located, and as you click you can see the highlighting or the border changes, so engine speeds there. This is particularly useful to share between participants in a networked control scenario so that you all share the same specification. You can see here that there's quite a few messages in the J1939 DBC. So we'll go ahead and create one for our purposes here. So I'm going to create a new message, insert message, and I'm going to call this my TX message, and I'm going to put the ID in hex. It's going to be let's do 123. We'll use a standard ID, and we'll just put a couple fields in here. We'll do engine speed. This is your endianness. I'm going to use Motorola so it's easier for us to look at. And you can specify the start bit here. You can see here that it moves when I specify that start bit. I'm going to call it, I make it a 16-bit field. And you can specify any scaling that you might want to have. And you can see here the layout of that signal. I'm going to create another one. And I'm going to put this one at start bit 0, so that's way down there. And this particular one, since I want to have it go negative, I'm going to apply an offset to it, so it can go negative for the temperature. So I'm also going to create a message that we're going to receive. So I'm going to insert a new message. Actually, I wanted to have that ID 123 hex. Sorry, 123 hex. Okay, and this one's going to be 234 hex. And I'm just going to put a signal count in this one, and it's just going to be also the Motorola, and it's going to just sit in that first byte there. So that can go from 0 to 255. So I've created now my DBC, and I'm going to save this into my my MATLAB folder there, where I have my CAN folder. So I have now created a DBC file that I can use in my model, and you can see it showing up in my CAN folder there. So now I want to add a CAN message to my my model. So I open up my Simulink library browser here, and because I installed and integrated onto the MathWorks path, I see the New Eagle Network Toolbox here, and I want to do a transmit. So I grab the TX message. I should also mention when you buy this product, you receive a license dongle, and so the installer that we just ran installed the licensing component for this dongle, and you can see here Network Toolbox, it's a permanent license. If you have a dongle and you've purchased your license after you had your dongle, we will add the license to your dongle, and you can update it online here. Just hit update, and it'll pull your license from the internet and apply it to your dongle permanently. So it's saying that it can't find the example one. That's fine. It comes pre-configured with one so that it can show some fields here. But let's associate this with my DBC, the one we just created. And so now that I've assigned it to, or I've associated it with the DBC file that we just created, I've got my two messages there. And you can see that it knows about the ID that we associated with that message. You can specify, in our message it's not completely filled, so there's some open bytes. We can specify how to fill those bits, set them to 0 or set them to 1. Certain protocols such as J1939 specify that you must fill unused bytes in a certain way. We are able to specify which CAN bus we want. So here I have CAN 1. I should go ahead then and make sure that I have a CAN definition block for that CAN bus. So I'm going to add that CAN bus CAN definition there. Okay, so I've got CAN 1 now associated in my model. So I'm going to have that at CAN 1, and I'm going to specify a transmit rate of 50 milliseconds, we'll say. Now, the -1 that was there, that's asynchronous, so that the message would be sent each time the subsystem that contains this block is executed, so that would have been at 5 milliseconds. A couple other things about this interface before we proceed. If you have a number of fields in your message and you only want to send a few of them, you can disable them here. That's important, and you can see here it just it updates the mask there. That's important because if you're not going to be sending the fields, you can use the unspecified bit action to fill their values, and by deselecting the fields, we actually won't generate the code to pack that field, so it creates a more efficient embedded implementation. So it's important to consider that. Here we're going to send both of them. You can also, if you're using the J1939 protocol, you can specify a couple additional ports on the block. So that protocol specifies that the ID has a couple of special fields within it for destination and source. And so you can, by clicking these blocks, you can add a couple ports to the model or to the block here, and that'll allow the ID to be updated dynamically using the value on those ports. So now that I've selected my message from the DBC file, I would plumb in the signal values from the model. For the purposes of this demonstration, I'm going to go ahead and just hook up some data from a sine wave generator. So for RPM, I'm going to give it an amplitude of 2500 and a bias of 2500. So that'll create a sine wave from 0 to 5000. For coolant temp, oh, by the way, since we specified an offset there in our DBC, it's able to go from -40 to 215, and that's because it's a 8-bit unsigned data type. So for this one, I'm going to have an amplitude of 100 and a bias of 90. So that'll allow it to go to -10. Okay. What I do need to specify an inherited sample time there, so just for the sine waves to work with the in code generation. So now I will have created a model that this simple model here will just go ahead and send out the kind of simulated values of engine speed and coolant temp on message 123 standard 11-bit at 50 millisecond rate, at a 50 millisecond rate, and it'll fill the values into these fields. It'll be useful for us also to see how the receive functionality works. So I'm going to create a subsystem just to kind of arrange the transmit message there, and I'll go ahead and create a receive message. So I want to associate that with my DBC in my CAN folder there. I've got my receive message. It's going to be ID 234 hex. I've got my one signal there. Notice that there's no transmit rate because we're going to be receiving it. One thing that you can do on the receive side is add an age count, which will tell you how many times has this block executed since it received a fresh message. So the first time that it executes when there's new data, that will be 0, and then the next time it would be 1. You can also use the data available port. So by adding these, you see we've got data available and age count. So those will tell you when there's fresh data available will be true one time for each execution of this block with a new incoming frame, and age count will count up. And then count is just the value that's coming in. So what I'm going to do is go ahead and hook some probes to these. Now, since I've asked the block to label the output wires with the field names, I can add that the name source is the input wire on my probe. And hook those up, and if I hit Control D, it picks up the names, data available, age count, and count. So this is ready to receive this message. I wanted to also mention that if you're familiar with the MotoHawk CAN slots, you can identify this receive message with a slot here, and then you can use the slot triggers. You can also specify a queue size. A queue size is useful if there's a transmit message on the bus that's kind of bursty. So if your foreground rate is executing at, say, 20 milliseconds and this message is coming out at a multiple of that, and so you may have the message on the bus multiple times between an execution of the this block. A queue will allow the messages to queue up, and then you can do a do while loop on the data available port to kind of empty that queue out in a single time step. So that's another useful feature there. And then also mask. If you want to receive multiple IDs with the same block, you can zero out portions of the mask. So for instance, the way I now have this configured with 7F0, it will receive all IDs of 230 hex through 23F. So that can be useful in certain scenarios. I'm going to go ahead and put that back to 7FF. So now we're almost ready to do a build of this model. I'm going to go ahead and organize the RX also under here. The only few things that we need to do a build is, first I need to set my compiler. I'm not going to be using the default Greenhouse compiler. I'm going to be using the free GCC compiler with this build. And then the last thing we need to do to use the network toolbox is go to our CodeGen options, and we have to make an update to the make command here. This is done once for this model, and then it's saved from there on out. I just apply any underscore before the make command, and we should be ready to build. So I'm going to kick off a build with Control B. And what this is going to do now is it's going to generate code for this model, and then it'll have a bunch of C code and header files, and it'll go ahead and link that against the pre-built components of MotoHawk and create an executable that I can load into my ECU that I have on the bench here. And this will take maybe a minute or so to complete. And while we're waiting on that, I wanted to show with the installation of the network toolbox, there's a user guide. And that goes through the installation process for the Toolbox, shows the view that you have of the Toolbox in the Simulink library browser and what the blocks look like in a model. And probably more useful, it goes through each field on the block interface, the dialog that you are presented with, and provides some information for each field. So you can just follow the numbers, and each field has a little description, and there's also some helpful hints there. So you can find that user guide in the installation directory, Program Files, New Eagle Network Toolbox. So our build completed. So now I have an executable that I can load into my ECU, and to do that, I'll load it with MotoTune. So I see I've got my SRZ file there. I'm going to program it into PCM1. And off it goes. Okay, so programming was successful. Now, since we have a message that we're transmitting, I want to show that the raw message, and a tool that we frequently use for CAN development is the Kvassar CAN King. So that allows me to go online. I'm at 250K baud, and you can see that I had defined that here in my CAN definition block. And I'm going to go online here, and you'll notice that the ID here is shown as 291. That's because I don't have my hexadecimal text formatter on, so I'm going to add those. I'm going to put the delta time there so that we can see what the delta time for this message is. And so we see the message that we are sending out, 123 there. Might be useful for me to pull up our database viewer alongside this, so that we can see our transmit message and how it's laid out. So we see here our first 2 bytes are moving along in a sinusoid there, and that's our engine speed here. And then this last byte is our coolant temp. And we can see that's also moving in a sinusoid manner. We can go to fixed positions here, and that'll hold that message at a constant row in this viewer. And we can see that the delta time is 50 milliseconds. And that is as it should be based on our interval that we specified here in the model. So that is kind of a quick overview of the transmit side of things. So let's look at the receive side of things. In order to do that, we're going to need to go online with the ECU using MotoTune to look at the value of these probes. So I'm going to open a new display with MotoTune. And we see in the foreground we have some probes under the RX subsystem. And so I'll drag those in. We have first the data available field, the age count, and we can see that there's been at we're running this foreground rate at 5 milliseconds, which is the default. 5 milliseconds is the default RTI periodic. So we see that there's been 38,000 executions since we've received a message, and since we haven't received any messages yet, that's just the count since we started executing. So in order to get that message on the bus, we can use CanKing, and so the message we need is 234 standard, and that's in hex. So I'll leave these, pull these up so we can see. We can use the CanKing universal message, and the ID we want to send out is 234. And when I send that, we see that the age count reset. Data available probably went true for some period, and our count is 0 because we have 0 there. Let me go ahead and set these to fast. Oh, I should also mention there's a couple of other messages that we're seeing here in our data viewer here, and they're running along, taking up most of the traffic on the bus, and that is the traffic from MotoTune here. So I'm going to go ahead and use my filter here in CanKing. Under the hardware filters, there's standard filters and extended filters, and we can use mask and code to kind of filter the data that we see. For this purpose, I'm going to just turn off the extended IDs, and you'll notice that when I clear, then those other messages are gone. When I accept again, we see them show up. So I'm going to turn those off so that they don't get in the way. They're still being transmitted, we're just not seeing them in this view here. And when I send my message here, I see it show up on the bus here. So I want to also pull a chart so that we can see in MotoTune the values. We've got these 3 values that we're viewing, and this is the age count climbing away. And when I hit send there, it goes back down to 0. Now, if we want to look at the data available, we can do that more easily by removing this signal. We'll remove that one and open our chart. So now we only have those 2, and when we send that, we may have to send it a couple times because the data available is just a simple flag that's going through every so often. There we go, we got a spike. The sampling frequency of MotoTune is 50 milliseconds, and the execution rate of our foreground is 5 milliseconds. So that flag's being cleared very quickly. Okay, so now we can go ahead and fill in some data. We've got this message we're receiving. This first byte is our field here, count. And so if I go over to my transmit window here and I put in, say, 10, we can see that our count field went to 10. We can see the value there, A, which is hexadecimal for 10. We could turn that to decimal and see that. 10 there. And I can, of course, change that. So that is kind of a quick overview of how the receive blocks work. And also how to do some basic CAN development using CanKing. And so what I'll do is I'm going to go ahead and zip up the model that we've been working with here today, and I'll post that onto our wiki so that you can reference it for any questions you might have. And it looks like we don't have any questions in the queue, but I do want to thank you for your attention today, and lastly point out that There's more information on our wiki site at neweagle.net/support, and you can find out more about the New Eagle Network Toolbox as well as other products that we have for CAN networking there. So thank you for your participation today, and join us again next month for a webinar on our CAN data loggers, particularly our embedded data logging appliance, the VCAN 320. Thank you. Bye.